This is the first of two videos on counting partitions. This one is relevant to the problem that you have on the online homework, and the second one will be relevant to the problem that you have on the writing assignment. In this first part, we're going to count the number of partitions of a set of numbers into a specific number of parts. The notation for this that we use is S and K, and I know the S doesn't stand for partition. S stands for Stirling, who was a 18th century mathematician that worked on this problem, not in a combinatorics context, but we have named these after him. Anyway, so N and K are respectively the size of the set we're partitioning and the number of parts that we're partitioning into. If we make a list of all the partitions of a three-element set, as I've done here, you can see that some of them have one part, some of them have two parts, and some of them have three parts. These are it's the same notion of partition that we studied back in section 3.2. So there's only one partition of 1 through 3 into one part, the set that just includes the entire set itself. There's only one partition that partitions this into three parts, namely making each of the numbers in its own little singleton set. And then if you're allowed to use two parts, then we have three different partitions that we can make. And so we would say that the number of ways to partition it into one part is 1, the number of ways to partition it into two parts is 3, and the number of ways to partition it into three parts is 1. So these are the partition numbers. If we think about smaller values of n, the examples are sort of silly, but we know from our study of recurrence relations that we do need to know what these small values are. So for example, if we only have a two-element set, then there's only two partitions you could have. If you only have a two-element set, you can either keep everybody together in one part, or you can give everybody their own part. So these are the only two possible partitions of the set 1, 2. The first one is into one part, which would be this guy. The second one is in two parts, which would be this guy. And so there's one of each. That's what that's telling us. This one is not too hard to see that if you only have a one-element set, then the only possibility is just to make that one person be their own group. So there's only one way to do that, and it has one part. This last observation that S00 is 1, that seems very strange that we should be able to interpret something like that. But there is such a thing as a zero-element set, which is the empty set. And so partitioning the empty set is at least something where the question makes sense. And if you think about the specific technical definition of a partition, then the empty set itself is a partition of the empty set. It's not worth worrying about in general because that's a very strange particular thing that happens only with the empty set, but yet there it is. So it does happen. There is one way that actually happens. So now we have all these small values of the partition numbers. We can think about how do we form all of the partitions of a certain size of a larger set. So our example of doing this recursively is going to be to compute S43. Remember, in S43, it means this is the number of things that we're going to partition. So in our case, we'll just use 1, 2, 3, 4. It's the easiest four-element set to think about. And then this is the number of parts. So 3 parts. So we're going to try to form all of the partitions of 1, 2, 3, 4 that use 3 parts. To do this, I'm going to need to refer to the partitions of the three-element set that I got before. So I'm going to lay these up here. It's exactly the same thing I had on the previous slide, just so that I can refer back to them. All right, so if I want to form partitions of 1, 2, 3, 4 into 3 parts, I'm going to break these into two cases. The first case is to take one of these guys that has 2 parts and then just add the singleton set 4 right into the list. So that's a really easy way to create a partition with 4 parts where I am using all the numbers 1, 2, 3, 4. I'm going to take each of the partitions that I have. Where's my thing? Right. So I'm going to take each of these partitions that I have with 2 parts, and I'm going to add this singleton set 4 as a new third part. And so that will give me a bunch of partitions of 1, 2, 3, 4 that have 3 parts. All of those, the thing they all have in common is that they all use the singleton set 4. Now I need to count partitions of 1, 2, 3, 4 that don't use the singleton set 4. Well, I can also form those from the list I have before by looking up here for partitions. Oops, let me get my pen. Look at partitions of 1, 2, 3 into 3 parts. So this guy right here. And then add the element 4, so the element 4, into each of these parts. So I could add the 4 into the same part as 1, and that'll give me one option. Or I could add the 4 into the part that has a 2, that would be another option. Or I could add the 4 into the part that contains a 3, that's the third option. So I'm not going to do all 3 of those at once, but that gives me 3 different partitions that I could make where the 4 is not by itself. So in other words, the 2 cases are, we're going to count the partitions when 4 is by itself and the partitions when 4 is not by itself. When 4 is not by itself, that means it has to be inserted into one of the ones I've got up there in the red box. Okay, so let me just show you like if we really do it. In case 1, I said that I was going to add the singleton set 4 to a partition into 2 parts. And so again, these are my partitions into 2 parts. So I've rewritten them here. And then all I've done is add in the singleton set 4 to the partition, and I get these 3. And so these are all counted by S43. Those are partitions of 1, 2, 3, 4 that use the number 4. So now let me illustrate case 2. I'm going to add the number 4 into any of the partitions of 1, 2, 3 into 3 parts. For us, that's just this one. You can see how this would work regardless of how many of these you had. You'd have to do this for each one. But when I have the set, the partition singleton 1, singleton 2, singleton 3, that's now going to give me 3 different partitions of 1, 2, 3, 4 because I get to decide where to stick the 4. I'm going to put the 4 in with one of the 3 parts I already have. So the thing that all of those have in common, all of these have in common, is that the 4 is not alone. Right, so the 4 is not there by itself. So case 1 counts all the one where the singleton, the new element that I have available is in a singleton set by itself, and then all the ones in case 2 are counting the ones where the new element I have available is in with something else. Oops. And so the number of ones I have in case 1, that corresponds exactly to S32, because S32 was this many, and so I have one of these new partitions for each one of those. Over here, I have 3 times S33. S33 was a partition of 1, 2, 3 into 3 parts, and then I could pick any of those 3 parts to add my new element 4 to. And we know S33 was 1. So the final conclusion is that S43, if when I add these cases, I'll have however many partitions I have in S32 plus 3 times the number of partitions in S33. And so in this case, that's 6. This is what the general argument looks like. This is exactly the same thing that I wrote down, but now instead of it being about S43, this is now about SNK. So I'll let you just look at this and try to match this up with the example we had before. And the problem that you're working on for the homework, you don't have to derive this relationship. You just have to use the relationship. So this is the takeaway, that this is the recurrence relation that we get. Hopefully you can see now where this comes from, that these are the case 1 partitions. Those are the ones that have the new element as a singleton set. And then these are the ones with our case 2, which are the other type. But because we have this recurrence relation, and it's 2-dimensional in some sense, it's got an n and a k in it, then we can make a table, much like a Pascal triangle looking table, out of the values here. And so if I have my row numbers being my values of n, So that's what I'm thinking of here. These are my n's, and then these are my k's. Then I can create this table by just using the recurrence relation. So for example, the reason I know this is 7 is this is S42, meaning that n is 4 and k is 2. If I read the recurrence relation I have above that says S42 should be S31 plus 2 times S32. Again, I'm just reading this. I'm reading that exact thing, but I'm reading it where n is 4 and k is 2. And so if I do that, it says this. Those refer to numbers that are higher up in the table. So S31 is 1, and S32 is 3, and so 1 plus 2 times 3 is 7. So that's where that value comes from. So I can extend this table down just like I can with Pascal's triangle. Notice that these initial values over here and down here are kind of silly. The fact that those are always 1, that's an easy thing to see. If you're only doing a partition into one part, then there's only going to be one way to do that, which is everybody is in the one group. Similarly, if you say I have n people and I want to form n groups, there's only one way to do that. Everybody has to be their own group. So at those extremes, where you only have one part, or you have the number of parts equals the number of people, in either of those cases, the number of ways to do that should be 1. So that gives you the 1s down the sides, just like in Pascal's triangle, and then this recurrence relation would allow you to build in the values in the middle. So in the online homework, the questions you're asked are to understand what those sort of extreme conditions are, and also, when you get a little bit off of those extreme conditions, you can also reason things out. For example, the number of partitions of 1 through 6 into 5 parts, this number down here, for example, that's something that's actually easy to count if you think about it without having to build this recurrence relation in this whole triangle. That's not a very hard question, because if you have one less part than you have people, then that means that your partition has to look a very particular way. It has to look like a whole bunch of singleton parts and then one part of size 2. That's the only thing it could possibly look like. And so if you think about how to count those, it won't be strange that the answer to that would be 15. I think that's it, all that you need to know for the homework. So hopefully that helps give you an idea of how to approach those problems.